Hello and welcome to our 25th FAIRWork webinar, 26th FAIRWork webinar. We are now on the end spurt for our webinars, and today our colleague from UNM Research will introduce digital human factors and how we use them in FAIRWork. So how we can gather information about humans, about their physical and physiological aspects, and use them in decision making to further their well-being. And without further ado, I hand over to my colleague, and the stage is yours, Lucas. Thank you very much.
Okay, thank you, Christian, for the nice introduction. Welcome to this webinar. For all who don't know me, my name is Lucas Paletta from UNM Research, and I will present the webinar on the digital human factors in production, giving some wearable-based insights for resilience and stress management in general. And this presented work is based on a cooperation with my kind collaborators from the UNM Research Digital Institute. Now, digital human factors analytics is very much in the context of the framework of European gathered Industry 5.0, which is giving attention to the workers' well-being and fosters a human-centric technology development. And one major focus is to support the workers by building resilience on the workforce. The digital human factors in this project, FAIRWork, is therefore on measuring stress and resilience in order to avoid any toxic stress and to enable both human workers and also decision makers to be more resilient overall. That means to be capable to respond appropriately if any short-term, mid-term stressful work would arise. Now, these digital human factors analytics refer to applications in the project to two major use cases. Firstly, we refer to the use case workload balance that the research department CRF of the car production company Stellantis is interested in. And the individual workers are associated with, so to say, resilience scores that reflect the physiological strain of the workers, in particular with respect to intensive and long-term physical work. The physiological strain can be measured in terms of, for example, heart rate, skin temperature of the worker, and so on. Secondly, in the use case worker allocation, that, for example, electronic production company Flex was interested in, we measure the cognitive emotional stress. The focus is here on, for example, operators on the shop floor, could also refer to the decision fatigue of decision makers working in front of a screen for a long time. And this may be measured using heart rate as well, heart rate variability for stress, skin temperature, attention scores, and so on. And finally, of course, ethics and kind of persona management, I will come to this later, are mandatory to apply human factors management in FAIRWork, so to say, innovative democratic decision processes. For the FAIRWork project, we are focusing in the manner of explorative research on three different digital sensor technologies that are unobtrusive to some degree. Biosignal sensor shirts, eye tracking glasses, and so-called fitness trackers or smartwatches being equipped with high-quality biosignal sensors. And the interpretation of the raw sensor data is applied within AI services that should be finally explainable, assuring a trustful, transparent operations, and finally map to certain measures of cognitive and physiological strain, as well as eventually also effective and motivational state parameters. We need this to relate to any objective function of interest, such as for stress reduction, consideration of well-being, safety, motivation, and so on. And of course, finally, we will apply these functionals to optimize overall industrial processes where the work is embedded in. We were now very curious in the project about whether these wearable technologies would be accepted for the daily use at the workplace or for a study or even for a longer time. And for this reason, we presented the wearables to the workers and decision makers at the production site of Flex in Alkoven, Austria, and asked them directly whether they would wear any of these technologies during work. As you can see in the upper diagram, the majority agreed to use the fitness tracker or smartwatch and the shirt during long-term periods, whereas they rejected the glasses, but this is only due to the fact that we presented this jointly with an outwards oriented camera, which we don't need necessarily. So without, they would maybe agree as well to use that. Finally, high mental demand was reported, as you see in the lower diagram, as a daily load by many, preferable by decision makers. And bottom right, we report the really highly useful discussions at the FAIRWork fair and workshop together with lead decision makers and workers at the other flex factory in the project in Timișoara, Romania, that provided the important additional clues on what to care about. We implemented in the project the intelligent sensor box that is an architectural component with encapsulated data collection and analyzing services. And the real purpose is to measure via sensors that are attached primarily to the human as well also to the workplace, but keeping the privacy of the data. And only anonymous data are transferred to the overall system's knowledge base or top for further processing. And we implemented the following intelligent services, the AI-based physiological strain estimation, as well as a heuristic version of the cognitive emotional strain estimation. Furthermore, resilience score computation component and expert and developer dashboard, we'll come to that later, for monitoring both raw and also metadata in effect over time, interface to the knowledge database, and the concept, at least for persona clustering. Inside this framework, the computation framework of the intelligent sensor box, we implemented a sensor module to the left in the larger frame with the communication handler and the engine for a research and development dashboard. The raw signals are grabbed, filtered, and forwarded to two major processing streams. The one is already visible in the right red box on top. It's related to the risk stratification for physiological strain, providing a strain index and the rule base also to determine risk level recommendation, for example, for pulse management. And the second one below is related to the cognitive emotional strain on processing chain, again, with risk level management. And now a central focus is on the resilience score that is delivered to the project's architecture to serve these advanced higher level optimization processes. Resilience, what is it? Is a long-term stress effect and basically characterizing the response behavior on stressful events. The long-term stress and resilience have further consequences on production activity. This is published also by other groups, researchers, due to the reported positive correlation with errors and periods of distraction at work, reducing the quality and performance of the work and leading to, in this sense, new costs and losses for companies, also given by the corresponding increase of sickness leaves and absenteeism. Was reported. Now, the intended application of the wearables is in two environments. Firstly, in explorative manner at the human factors lab, and secondly, it's still intended to apply them later at the manufacturing site at Flex. Our model, the framework for stress and resilience factors, extends several previously defined models, actually, such as the transactional model of stress and coping with stress, cited bottom right. The functioning of our model is designed as follows. We'll give some detail. The task demands generate strain in the worker that we measure using biosignal sensor-based wearables by means of physiological strain, PSI, as well as cognitive emotional strain, CES. And the long-term stress of both types would increase the mental exhaustion score or the need for recovery, which in turn has a substantial impact on the overall psychological resilience score. However, it can be empowered by the contribution of specific resources, parameterized in the sense that finally impacts a coping capacity. And any recovery processes will eventually reduce the need for the recovery and could be measured, for example, with wearables by its sleep features. Now, let's just quickly have a close look on the background of computing the resilience score. I don't want to go too much into detail. We determine this daily strain score by integrating contribution both from one hand physiological as well as from the cognitive emotional strain and apply a saturation function. And in the next step, we assign a time window in which we consider all these daily stress measures that would definitely contribute to impact the state of the day that follows this time window in terms of impacting the dimension of the need for recovery on the subsequent day. So as a kind of time-based effect. Contributions within this time window are weighted by recency, discriminating between long-term and short-term effects on the need for recovery. And finally, the resilience score, as it is, must correlate indirectly with this need for recovery. And in addition, input of additional resources, physiologically, mentally, might add, in theory, to resilience. And with this adds to the capacity of coping with stressful situations. Now, our human factors lab at UNM Research, which we have run exploratory studies, provides numerous opportunities to study the impact on human factors in human-machine interaction in general and different business areas using digital sensor technologies and the kind of cognitive computing services. And this is often with the goal to provide also real-time assessment and feedback, and from this to be able to shape the design of the human-machine interfaces of the technologies in the direction of intuitive human-machine interaction. Now we'll watch a video with a demonstration of the biosignal wearables to measure strain in the human factors lab. Here are eye tracking glasses from pupil labs with front camera for egocentric scene videos and eye tracking from infrared eye-oriented cameras. The cable from the glasses lead to a smartphone that collects the raw data and sends them to the research server for analysis, and the smartphone can be conveniently attached to the body. The German Garmin is a highly unobtrusive wearable providing biosignal sensor data about cardiovascular information, psychological resilience, and the Q Smartshare that you see here also provides the cardiovascular information from fibers leading to a Bluetooth hub connected via smartphone to the internet. For a more precise computation of physiological strain, the so-called core sensor, a skin temperature sensor from GreenTech that you see here is required, can be easily attached to the body. Now, our colleague, as a test person in the lab, is now during the baseline measurement that could be taken early in the morning or at a quiet place where you pause. And to the left, you can see real-time the expert developer dashboard developing for the monitoring of vital signals as well as the physiological strain index signaling during baseline. All values are within the lower strain. Later, during an activity that incorporates a dynamic load, lifting, putting down 2 times 20 kilo dumbbells at the same time, the values, as you can see, are increasing over time. On the table to the left, just a textile strap-based sensor device that now this replaces the shirt, more comfortable. And meanwhile, with consistently ongoing dynamic load, the physiological strain index has continuously increased. Therefore, the risk level entered yellow zone, and recommendations for taking rest or hydration actions have been triggered. This altogether is considered an interface for the decision support system. Here we can see in the top diagram the raw data, such as heart rate in red and respiration rate in blue, as well as metadata in real time. Here the physiological strain index PSI star in green. And the mid diagram shows physiologically defined short-term and mid-term risk levels. In semaphore visualization, we can see that the PSI risk level turned to yellow to alert. And the lower diagram displays the triggering of recommendations, for example, to rest or to increase hydration through liquid supply, such as a bottle of water. Here's, for example, a short video of the scene camera just to see how the eye gaze is overlaid, the orange point. Eye tracking glasses are used in explorative studies, and extracted eye movement features would soon provide more information on stress in cognitive emotional process. And here's the resilience monitor that captures for each worker the stress profiles within a time window of 20 days. Red is the physiological strain, blue cognitive emotional strain from left to right, and green below the resilience score. Tendency goes towards higher resilience, as you can see over time. Now the data of the lab session representing the day today is uploaded, and as a result the stress jumps high, but the resilience score of course FAIRWork due to its inbuilt inertia model. Finally, the latest data are uploaded to the knowledge base for further decision making, such as applying the relocation. Just briefly, for the computation of physiological strain, represented by this PSI star index from wearable sensor, a key issue is to estimate the core body temperature very well. Now, our approach for this was to use existing study data from trained professionals, including data about gold standard wearable sensor data, as well as ground truth data of the core body temperature from gastrointestinal pills that they swallow. We computed a regression between skin sensor data and core body temperature, internal temperature, and compared 26 kernel-based machine learning methods. And actually, the Gaussian progression regression, or GPR, clearly outperformed other methods, including neural networks and trees. And this AI type GPR is also available in an explainable AI version with local explanation, which reveals the feature contributions to the prediction of each sample, while it maintains the predictive performance of GPR. In addition, one could consider also variants of this method that could predict strain in the future. But not yet outlined. The two curves in the top diagram demonstrate the difference between the actual core temperature in blue and the GPR, a little bit noisy estimate, but still very, very close with very small deviation on this kind of data set on test data. In the middle, the difference between ground truth and estimated physiological strain for a linear regression model to the left and GPR-based model to the right is sketched. And the table at the bottom gives a detailed account on the error measures to characterize the performance of the linear versus the GPR-based model. And the valid data to the right are those data underlying the GPR model that predominantly excluded outliers, so remove the outliers before. Now, human factors have significant impact on the human decision-making performance. Cognitive emotional stress will quickly impact on the decision quality under stress. Intuitive and therefore often suboptimal decision-making is preferred, and kind of tunnel attention predominates. The information overload, decision fatigue significantly decreased joint human-machine system performance. In explorative studies with cognitive emotional strain, we applied the sequence of 3 tasks: a baseline session without substantial activity to the left, a stimulus reaction choice called a task called determination test in the middle, the center, and the task to the right that is known to challenge cognitive load heavily. That is the MBAC task, it's called like that, working memory task that requires excellent short-term memory to appropriately react in time to a sequence of images presented to the operator. What you see here, a real-time monitor with the working memory task that is analyzed with an operator video to the left, being synchronized with the video of the egocentric camera, top left, oriented towards the tablet screen with gaze visualization in real time. And to the right, real-time raw data output of skin temperature, heart rate, eye tracking data also, and based on a cognitive load score. And with the resulting metadata stream represented by a so far heuristic index for integrating to a cognitive emotional strain score. Below, again, the synchronized risk stratification and traffic light representation, we can see that there's already kind of going to the top of some cognitive load in red risk level. Now, how can we just briefly mention that quantitatively measure the recovery from stress using physiological data? And this is often called a bouncing back effect, describing how quickly and effectively the autonomic nervous system returns to baseline, called homeostasis, after a stressor happened. And one of the most straightforward ways to track this is by observing the heart rate recovery. This simply looks at how quickly the heart rate drops after a peak induced by the stressor. The larger this drops and the faster it happens, the better the physiological recovery or the short-term resilience. Let us now see some typical examples in this respect. To the left, here different recovery responses relate to various intense physical activities, for example, running distances of 3.5 kilometers with 3 different intensities: lowest intensity, middle, and the top curve is the highest intensity. And you can see here to the right also representation of a heart rate recovery over time going down after 6-minute walking test with exponential fitting. So this is important for the model of different recovery responses of 2 significantly different subject groups. And the modeling of a very sense cognitive emotional recovery is fundamentally possible, but not well established. Research has so far focused mainly on purely physical recovery. There are few existing approaches show that the heart rate variability, which is inverse to the stress dimension, can also actually decline exponentially after mental stress. The decline means the stress goes up. The stress score making recovery rates with a decay parameter K, so to say, measurable. There's a clear research gap. The forthcoming study might therefore make an innovative contribution by applying exponential recovery estimates, recover them in the context of cognitive emotional stress at the manufacturing site. And this schematic sketch now illustrates our conceptual model for calculating the digital resilience score based on wearable data. You see at the core, we are measuring 2 main dynamics. Firstly, accumulation of mental fatigue, and secondly, the ability to bounce back that we have seen before via recovery events. And these psychophysiological constructs are tracked using wearable biosignals, such as the one shown in the image, the fitness trackers. And here on the top pass, we see how sustained mental fatigue leads to an integrated allostatic load, as it is called, the physiological burden resulting from chronic stress. And on the bottom pass, we capture recovery events, which reflect how well a person returns to baseline after stress, contributing to a so-called recovery stress state. And both of these streams, load and recovery, are statistically mapped to compute global scores, and these scores represent a more holistic, a general picture of an individual resilience. On the right, we differentiate between 2 outputs: the objective resilience score, which is derived from physiological and behavioral data, and the subjective resilience score, based on self-reports or digital surveys. And together, this dual score approach eventually enables personalized feedback and the potential for adaptive interventions based on a current resilience status. Just in order to quantify psychological resilience and stress in the workplace, we rely on a set of well-established psychometric instruments, questionnaires that could be applied. For example, the Resilience Score 13 provides a brief but effective way to measure the personal resilience. There are also shorter form, the RS4 of this questionnaire, especially in manufacturing, and captures the resilience traits like adaptability and self-acceptance. The CD-RES is most widely used and offers aspects like persistence and stress tolerance. The brief resilience scale is focusing on the outcome, how quickly someone recovers from stress rather than the traits. And there are others like perceived stress scale is about highly perceived stress that suggests low resilience. The rescue work question is particularly relevant for our project. It looks at the balance between experienced stressors like fatigue and recovery factors like rest and relaxation. Now, as a next step in the computational development, referring to actual future work, the scores for physiological, cognitive, emotional, and affective scores representing the so-called digital shadow of humans will be associated with specific task contexts and further result in machine learning-based clustering with respect to persona representations, such as for aged experts or for young rookies. And these are then related to a kind of decision-making that could lead to actions and adaptation in the overall social technical system. And in this sense, we intend to develop in the future human digital twins that can be used as operable and transparent representations of individual or in a holistic way, persona kind human decision makers and workers, and under the consideration, of course, of all necessary ethical considerations. Let me just briefly conclude by highlighting the key outcomes and our roadmap ahead. We've introduced a novel research protocol that fuses wearable physiological data with validated psychological assessments. And central to this is the advanced resilience computing model that we presented, which goes beyond static resilience indicators to capture the dynamic recovery processes, and that would enable continuous real-time monitoring of the workers' resilience risk and stress as well. And that would open the door to proactive and personalized interventions in industrial health management and just reflecting the well-being for each individual workers herself. And ultimately, we seek to validate this framework across varied industrial contexts over time to ensure its generalizability and impact on work well-being. And finally, I would thank all the co-authors for their valued contributions. And thank you for your kind attention. Maybe there are questions now. Thank you. Adrian, I give over to you.
Thank you very much, Lucas, for this interesting presentation. Are there any questions from the audience? Anything that should be discussed in more detail? I think this is unclear. So then, thank you very much. Thank you very much for joining, and hopefully see you at the next webinar. Then see you. Bye.
Bye-bye.
Thank you. Bye-bye.
Thank you.
Bye.
See you.